In today's video, I want to take a closer look at how sample statistics behave. In particular, we're going to look at how to calculate the mean, standard deviation, and variance of sample statistics. Now remember, a sample statistic is anything that is calculated or derived from a sample. Now every sample has to come from a population, so that's where this discussion really needs to start. So there's a population that we're going to take our samples from, and every population has its own parameters. Remember, a parameter is just anything that's calculated or derived from a population. So our population being sampled from, which is commonly called the parent population or the original population, is going to have its own population mean, mu, its own standard deviation, sigma. And if we look at a particular event, like getting heads when we flip a coin, there's a fixed probability of getting that outcome, of getting heads, right, which is the same as the proportion of outcomes that are heads. Okay, so mu, sigma, p, these are all population parameters. Okay. So the first statistic I want to look at now is X bar. So if we consider every possible sample of a fixed sample size, taken with replacement so that each selection is independent from the others, each of those samples is going to have its own mean, X bar. There are lots of different samples that we could end up with when we collect our data, so there's lots of different sample means we could get. When we look at all these sample means together, they form a population of their own. Okay? And this population of sample means is going to have its own set of parameters. Okay? So there is a mean of the sample means. That's the average of all possible sample means. And that is equal to the mean of the population that the samples were taken from. Okay. The population of X bars is going to have its own standard deviation, which is directly related to the standard deviation of the population we're sampling from. Okay, remember, standard deviation tells us how spread out we are. So what this is saying is how spread out the averages of samples are depends on how spread out the individuals were and how big the samples are. Okay. Now, similarly, the variance of X bar, right, is equal to the original variance divided by the sample size. The next statistic I want to take a look at is p hat, our sample proportion. So we talked about the event maybe being heads when we flip a coin. Okay, so if we flip a coin 50 times and we get 30 out of 50 flips being heads, then our sample proportion, p hat, would be 30 out of 50. Right? And so every collection is going to have its own sample proportion. And we take all the different proportions that we could get. All right? Those proportions, those p hats, will form a population of their own. And again, this population will have its own set of parameters. And so the mean of the sample proportions is equal to the true proportion, the actual probability of getting what we want in the original population. So again, if we talk about flipping this coin example, if the true probability of flipping a coin and getting heads is 1/2, right, then we expect in our samples, some samples will have a proportion of heads that's less than 1/2, some more than 1/2, but on average, it'll be 1/2, the true proportion or probability. Okay. So the next thing we want to look at is the standard deviation of p hat. And again, the standard deviation is how spread out the values. So in this case, how spread out the sample proportions are. Okay, so we're talking about here how far on average our sample proportions are from p, the true proportion. And that's given by the square root of p times 1 minus p divided by n. And if we square that, the square root disappears and we get the sample variance. Now, finally, I want to talk about the sample variance as a statistic. So every time we take a sample, we get a sample variance. And all those sample variances form a population of their own. And like all the other populations we talked about, there's going to be a set of parameters. So the mean of the sample variances is equal to the variance of the population that we sample from. Right? So again, that's some sample variances will be smaller than the true variance, some larger than the true variance, but on average, the sample variances will equal out to be the population variance. So far, these 7 parameters we've talked about, right, the 3 for x bar, the 3 for p hat, and the mean of s squared, they always exist regardless of the population we're sampling from, regardless of whether that population is discrete, continuous, skewed left, bimodal, uniform, does not matter. They always exist. Okay? Now, when we talk about the variance of s squared and the standard deviation of s squared, so these two, they don't always exist, and they vary from population to population. So we're not going to be looking at these, and we definitely will not be calculating these. So it's time to take a look at some very specific examples. So the daily high temperature at Maracas Bay Beach in Trinidad averages 82 degrees with the standard deviation of 6 degrees. Now, this is our population. Okay, so we want to find the mean, standard deviation, and variance of the population of all sample means for samples of 9 daily high temperatures at Maracas Bay Beach. So our sample size is 9. So we're saying if we take every possible set of high temperatures for 9 random days, every group of 9 days, every group of 9 high temperatures are going to have their own mean. And we want to look at the average of all those. Okay, so everything starts with the population being sampled from. Our original mean was 82. Standard deviation is 6, which means the variance of the high temperatures is 6 squared, or 36. So this is what we're given. This is the information we have about the population we're being sampled from. Okay, now we're being asked about the population of sample means. So applying the formulas we looked at previously, right, the mean of the sample means is equal to the population mean, so 82 degrees. Right, so some 9-day averages would be higher than 82, some 9-day averages would be lower than 82, but if we average out all those sample averages, they're going to average right back to 82 degrees. We were asked to find the mean, and now we're also asked to find the standard deviation. So the standard deviation of the sample means, so sigma of x bar, again, is equal to the original standard deviation over the square root of the sample size. So that's simply 6 divided by the square root of 9, right, which simplifies down to 2. So each average of 9 days, again, would vary from sample to sample depending on which 9 days we select. Sometimes the average of those 9 days would be higher than 82, sometimes lower than 82. How much higher or lower than 82? About 2 degrees, give or take. And finally, the variance would simply be, all right, again, 6 squared, 36 over 9, or 4, which of course we could just square the 2. Right? The standard deviation of 2, square that, we get the variance of 4. All right, now. Okay, so we're going to continue with the same example, talking about high temperatures at the beach. Okay, but this time I'm looking at the sample variance instead of the sample mean. Okay, so we want to find the mean of the population of all sample variances. Okay, so when we do this, we know the truth about the population we're sampling from, and the mean of the sample variances is equal to the variance of the population that we're sampling from. So simply 36 degrees. End of story. Okay, so let's take a second look, right, at these examples. So this time we're measuring the time it takes for the T, the hill route of the T, to make a full loop around campus. Okay, so on average, they take about 24.4 minutes with a standard deviation of 3.9 minutes. And we want to find the mean, standard deviation, and variance of the population of all sample means, okay, for samples of 128 loop times. And again, taken with replacement, which makes them independent. Okay, so the population that we're sampling from, which is where everything starts here, has a mean of 24.4 and a standard deviation of 3.9, and therefore a variance of 3.9 squared. The population of sample means, which is what we're trying to find the mean, variance, and standard deviation of. Okay, again, the mean of x bar is equal to the mean of the population we're sampling from. So that's 24.4 minutes. So the average of 128 loop times for some groups of 128 would be less than 24.4. For other groups, the sample mean would be higher than 24.4. But on average, all sample means for all groups of 128 would average out to be 24.4. Standard deviation of the sample mean is equal to the standard deviation of the individual loop times divided by the square of the sample size. Okay, so approximately 0.344, 714, 5558. And the variance would be, again, the standard deviation squared, so that's sigma squared over n. So 3.9 squared is 15.21 over 128. We divide that out, we get approximately 0.118828125. So one thing I want to point out, right, is if we squared the standard deviation, right, with all of the precision we had, right, then when we get that variance, we keep that precision, right, for several decimal places. But let's say the instructions had told us to round to 3 decimal places, and you rounded the standard deviation to 0.345, and you squared that. Now, when you square that, you get 0.119025, which rounded to 3 decimals, right, is 0.119. Okay, so notice that third decimal place, right, may not be the same at that point. So you always want to be careful, right, that when you round, right, you don't want to round rounded numbers. And so go back to the originals as best you can. So again, we're going to stay with the hill loop times, but looking at the sample variances. Okay, so we have our original population being sampled from, and we want to find the mean of all possible sample variances, right, for samples of 128 loop times. And so the population of sample variances is going to have a mean that's equal to the variance of the population those sample variances are coming from, which is 15.21. Okay, so these two examples show you how to calculate the mean, variance, and standard deviation for x bar and the mean for s squared. And the next two examples are going to talk about how to find the mean, standard deviation, and variance of sample proportions, p hat. In this example, we're going to roll a fair 20-sided die 100 times. And each time we're looking, right, for the die to come up with 20. So when we consider every possible sample of 100 rolls, it has a proportion of rolls that are equal to 20. Right? And that set of all possible sample proportions, again, forms its own population. And we want to find the mean, standard deviation, and variance for that population of p hats. And so, again, as always, everything starts with the population that we are sampling from here. Okay, so the probability of rolling a 20 is 1 out of 20, since we have a fair 20-sided die, numbered 1, 2, 3 up to 20. Right, and that's going to be 0.05. 1/20th is equal to 0.05. Okay. And so that's each individual time we roll. The probability of getting a 20 is 0.05. Now we're going to look at what happens when we roll 100 times. So we roll 100 times, we count up how many 20s we have, that's our sample proportion, and we look at all possible sample proportions. The mean of those sample proportions is equal to the true probability of the event happening each time we run the experiment. Right? And so that simply was 1/20th or 0.05. The standard deviation, right, is given by this formula. And so we simply have to insert the 0.05 for p, and the sample size here is n equals 100. So our standard deviation of our sample proportions, right, is given by the square root of 0.05 times 1 minus 0.05 divided by 100. And here's the decimal approximation. And again, that is saying how far on average the p-hats will be from the true probability of 0.05. So some sample proportions will be higher than 0.05, some will be lower than 0.05. How much higher or lower? Well, on average, about 0.02. And then, of course, the variance of p-hat is calculated simply by leaving off the square root, again, because it's the standard deviation squared. So plug in the 0.05 and then 100, and we end up with 0.000475. So let's look at one last example here. Okay, so every day, your statistics instructor brings a bag filled with 10 ping pong balls to class. 3 of them have quiz written on them. And to start class, the student pulls out a ball, and if the ball says quiz, you got a quiz that day. So every possible sample of 34 class days has a proportion of days that a quiz was given on. Okay, so that's our p-hats. And if we look at the set of all possible sample proportions, right, all the p-hats, all the things that could happen, right, you're going to have a population of its own. And again, we want to find the mean, standard deviation, and variance for this population. So the population being sampled from, right, are the individual days where you either do or don't have a quiz. And the probability of having a quiz on each random day is 3 out of 10. Because again, there's 10 ping pong balls and 3 of them say quiz on them. So when we start talking about p-hat, the sample proportion, right, and again, for some groups of 34, you may have 0 out of 34 quizzes. Other groups of 34, you may have 18 out of 34 quizzes. Right? All those different sample proportions together form a population. And the average of that population, the mean of that population, is going to be the true probability of having a quiz each individual day, which is 0.3. The standard deviation of the p-hats, so how far off? Again, some groups of 34 will have less than 30% quizzes. Some will have more than 30% quizzes. How much more or less? That's what the standard deviation tells us. Right? Again, all we got to do is plug in the 0.3 for p and the 34 for n, and we get approximately 0.078 and change. And the variance is calculated again simply by taking the calculation of the formula without the square root, again, because that's sigma squared, and that will give us approximately 0.006 and change. And again, you could square the 0.07859052448, and as long as you do all of that, then when you square that, you'll get the variance accurate to several decimal places. Just don't cut that standard deviation short. Don't round the standard deviation to 0.08 and square that rounded version. And that's how you calculate the mean, variance, and standard deviation for x bar and p hat, and how to calculate the mean of s squared. Good luck. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!